Welcome to this last lecture of this complex network theory and application series. So, we have been looking into the properties of citation network analysis, and last day we have seen that the citation profile of a paper can be categorized into at least 5 different categories, and then we have seen how we can use this idea in order to do citation count prediction efficiently. So, today we will further develop on this idea, and what we shall see today especially is, like all this time we have been looking into the link features mostly, that is we have been looking into the in degree and the out degree of the citation network. But then if you remember that each scientific article actually is a collection of a large volume of text. So, a scientific article can be thought of a corpus of text basically, and today we will see that if we can further use some text features in order to enhance the citation prediction model that we have already proposed. The stratification model that we have proposed in the last lecture, we will try to further enhance that model using certain interesting text level features. Okay. So, the two text level features that we will talk about today are one which we called COUNTEX, and the other is which we call cite words. So, basically if you look into the scientific document, okay, if you look into a paper, so you will see that the paper actually talks about some other paper at different points in the paper. Okay. Suppose you have a paper P1. Now, this paper P1 has, say, an abstract, then there is an introduction section, then there is a methodology section, then there is a result section, and then finally there is a conclusion section. Now, let there be two other papers, P2 and P3. Now, say for instance paper P1 talks about P2 in introduction, whereas it talks about P3 in introduction, in method as well as in results. Okay. So, this immediately tells you that paper P3 is actually more important for paper P1 than paper P2. Paper P2 is referenced only once, whereas paper P3 is referenced at least 3 times. Okay. So, this actually is the basic idea behind the formulation of COUNTEX. You basically count the number of times that a particular paper, in this case P3, is being invoked by some other paper in the entire set of references. Okay. So, this actually defines the idea of COUNTEX. So, the next idea, cite words, is basically also interesting. So, what you try to observe here, again you can take 2 examples, say P3 and P4, and say you have abstract, introduction, method, result and conclusion. Now, say the paper P2 is invoked only in introduction with many other papers, okay, and there is one sentence which paper P1 actually writes about all these papers together, whereas paper P3 actually is invoked in the method section and there is one full sentence that is dedicated to paper P3. Again in the result section there is one full sentence that is dedicated to paper P3. So, you basically find out what is the average number of words that is dedicated to paper P3, whereas what is the average number of words that is dedicated to paper P2. Now, here if there are like 7 words or 8 words, okay, 7 or 8 words in this particular sentence which invokes P2, P3, P4, P5, then these 7 or 8 words are actually shared between all the references, and you say that P2 on an average gets a share of 8 by 4, that is 2 words if there are 8 words in the sentence. So P2 gets a share of 2 words, whereas P3 probably gets a share of 2 words from the introduction. Say if here in the method section again, see if there are 8 words dedicated to P3, so 2 plus 8, and again in the result section if there is a sentence with 8 words, so then another 8 words are dedicated to P3. So basically the total number of words that are dedicated to P3 is 16 plus 2, 18, whereas the total number of words that are dedicated to P2 is just 2. So that means again this is an indication that P3 is probably a more important paper for P1 than P2. Okay. Now the question is, given this information, can we do our citation count prediction even better? So what I show you in these 2 slides is basically if you take papers from the different categories that we introduced last day, peak init, multiple peak, peak late, monotonically decreasing, monotonically increasing, you see that the count text value, that is the total number of times that a paper is being referred in the text by any other paper. So the categories monotonically increasing and late peak, these are the 2 categories that are at the that receive the highest count text values. Okay. So these are the papers which are invoked by other papers a lot in their text, a lot compared to all the other categories of papers. So basically again you see a discrimination between these 2 sets of categories compared to the other different categories. So in terms of count text, so you see that the count text values are usually larger for these 2 categories of papers. Similarly the cite words, again in the cite words you see the monotonically increasing as well as the peak late papers have on an average larger cite words than other categories of papers. Now if you introduce these 2 additional features in your set of features that we have already discussed. So we already discussed, if you look at the slides, we already discussed that there are some author centric features, some venue centric features and some paper centric features which you use to train your regressor. Now in addition to these features, if we add the 2 interesting and very different features that we have just now defined, the cite words and the count text, what we observe is that these 2 extra features allows us to obtain the R square, the rho and the theta that we also obtained earlier. The things that the values that we obtain using these 2 set of features, using these 2 additional features actually agree with our ground truth data far better than the 2 previous models. You remember we had the first baseline which had no stratification, the second baseline which had the stratification of the training sample into 5 categories, and then we have this third model which has the stratification plus additionally these 2 features, okay, the cite words and the count text. So including these 2 features, what we observe is that we further improve the R square, the theta and the rho values. So the agreement with the ground truth data is actually further enhanced if you use these very 2 very simple features based on text properties. Okay. And not only that, what we also observed, so if you remember in our last results we had looked at a time gap of 1 year, 2 year and up to 5 years. Okay. 5 years down the line what should be your predicted citation history, but inclusion of these 2 simple features actually allows us to predict reliably even after 9 years of publication. Okay. So standing at the current point in time, you can do a prediction of the citation count even after 9 years quite reliably if you just use these 2 simple features. These 2 features are very simple, but then since they are extracted from the text properties, they are very strong discriminative features and they actually give you a very good intuition about the citation count of a particular paper in the long time. Okay. So that actually gives you a brief idea of how the notion of categories of citation profiles of papers as well as these two simple text properties can enhance the task of citation prediction, which is used, as I said, in various different tasks like academic recruitments, university rankings, etc. So in the last lap of citation analysis, we will try to look into the citation history or the citation count or the citation behavior of what we call ancient papers, papers which are old, pretty old, say 10 years old, 20 years old. So we will try to see what is the citation behavior of these set of papers. Usually in the community, it is thought that as a paper becomes older and older, the number of citations that it gets becomes lower and lower, and that is what we also saw in our citation profiles. A majority of the papers actually classify themselves into the speak in it category, as we have already seen. So that's why the average behavior also resembles the peak in it category. So mostly in the first few years you will gain a large number of citations, and then it will actually decay over time. So that is what we have observed. Now, so in the rest of the analysis, we will try to delve a little bit deeper into studying the citation behavior of older papers. Is it really like that, or are there certain interesting further observations that one can make? Actually, I guess all of you are aware of this particular portal. So it's the Google, it's the standard Google Scholar portal, and of late Google Scholar has started writing this particular slogan on its portal: stand on the shoulders of the giants. So basically one would wonder why such a slogan is being reflected on the page of Google Scholar. So this actually is connected to this paper which was written by a set of authors who actually are the lead developers of Google Scholar. Anurag Acharya is the leader of this team, and they wrote a paper on the shoulders of giants, the growing impact of older articles. So in this paper what they show is that so older papers actually are gaining citations over time. So in general, community believes that older papers over time are losing citations. Okay, they are going into obscurity slowly and slowly, whereas this is a paper which tries to show that it's not always true. Papers which are 10 years old, 20 years old may get a large number of citations, so accrue a large number of citations in general, and that is what they try to do. They try to do using some quantitative data analysis and show that there are a large number of old papers who are getting a huge volume, who are attracting a huge volume of citations. So to make the difference clear, the usual observation in the scientific literature is that papers that grow older in time actually go into oblivion and obscurity. They continuously lose citations. Okay, whereas this is one particular work which tries to show that this is not true. They try to challenge this idea and try to show that papers which are 10 years old or even 20 years old actually accrue a large volume of citations. So this work actually attracted a lot of media attention, since the team of authors were trying to tell something which is very different from what is observed so far. So this work actually attracted a lot of media attention. So we tried to see, like, so and they make a claim which I am trying to state here in this particular. So I have just extracted the claim that they have made. So what they say is that 36% of the citations were to articles that are at least 10 years old. Okay, so basically what they saw is that a large fraction of citations are going to papers which are old, which are pretty old, which are like 10 years old. So this is what their primary hypothesis was, and they use interesting data analysis techniques to establish this fact. but then we tried to look into a little bit more details about this analysis. So we were kind of thinking like how these two contradictory ideas can be existing at the same point in time, while the literature so far has said that older papers grow try to lose citations over time and they go into oblivion and obscurity. These authors are telling that it's not true and that older papers actually attract a large volume of citations. So how to reconcile these two opposing observations? So the first thing that we did was we tried to look into two top tier conferences in the computer science area. So one of them is, as I already told you, is the data mining conference, ACMC KDD, International Conference on Knowledge Discovery and Data Mining, and which is the largest and the most important conference in data mining, in the area of data mining. And you have another conference, the Neural Information Processing Systems, which is a top tier conference in machine learning. So if you look at the most highly cited papers in these two conferences, what you see is that most of these papers are not very old. Most of these papers, so the highest cited paper is was authored in 2011, the next highest was authored in 2010. So these are only 4 or 5 years old. Okay, so the claim that the authors of Google Scholar were making, that most of the citations, the largest volume, the high volume of citations is going to ancient papers that are 10 years old, is actually not being observed, at least in this simple data analysis that we do. So the same holds for the other conference also. You see, for the other conference, the papers that get the largest number of citations are even more recent, okay, 2012, 2013, etc. So where lies the fallacy? So why do the Google Scholar authors observe that there is an increasing volume of citations that is going to older papers? And what we see is that what we essentially see is actually summarized in this particular slide. So Google Scholar authors were observing that the volume of citations that were going to older papers which were 10 years old or 15 years old or 20 years old, that is actually rising over time. Now what they did not consider is that the volume of publication is also growing exponentially over time. So this factor they did not count in. So it's not only that the citation of a paper is growing, but also the total number of papers published in a particular field in computer science is growing over time. So if you look, the profile of publications is actually also exponentially rising over time. So this factor has not been taken into account in their analysis, and therefore you get an observation like the one that they have seen, that is the total number of citations that is going to the older papers is rising, because the volume of older papers is actually rising over time. So since this volume is not this rising volume is not factored into the analysis properly, that's why you observe that there is a steady growth in the fraction of citations that is going to older papers. So in order to factor in this idea of growing number of publications over time, what we tried to do is we tried to fix a set of papers, and we tried to see, let us take papers which are 10 years old and only top 100 cited papers of that time, say papers which the top 100 cited papers which are 10 years old. Okay, take those papers and see what is the fraction of citations that are going to these top 100 papers. Okay, not the entire set of papers that are 10 years old. Okay, not that entire exponentially rising volume of papers, but to a fixed set of papers, only the top 100 highly cited papers which are 10 years old. If you look at that profile, you see that actually the fraction of citations growing to such papers is actually declining, which is opposite to what the Google Scholar authors observed. Okay, and it is not only true for the top 100 cited papers, it is also true for any random set of 100 papers. Okay, if you take a random set of 100 papers, random but fixed set of 100 papers which are 10 years old, you observe that the fraction of citations going to those papers is actually over a decline. So basically the hypothesis that people have already observed in the literature long back, that older papers tend to usually on an average go into oblivion and obscurity, is actually holding from our data analysis. The glitch that was there in the analysis made by this Google Scholar team is that they did not factor in the growing volume of number of publications. So that is, so basically when you are doing large scale data analysis, that the analysis could be, so this particular observation gives you an idea how tricky such an analysis could be, and you have to be very cautious that you are doing your analysis appropriately and correctly, especially while normalizing things. So then what we tried to do is like, so the Google Scholar team observed that there is a rising volume of citations, whereas we observe that there is a steady decline in the rate of citations. So can these two things be nicely summarized into one picture? So that is what we want to now do. So Google Scholar team actually saw, if you look at the unlimited volume of publications, the exponentially growing volume of publications, you observe that there is a rise in the number of citations that is going to older papers. However, once you make the set fixed, you observe that the fraction of citations going to this fixed set of old papers basically is on a decline. So now can you put these two information together in one single quantitative plot? Okay, that's what we will try to do in the next slide. So here we look into different venues in computer science. Sigmod is a venue which predominantly publishes in databases and data mining. SIGIR is a venue which predominantly publishes works in information retrieval. ICML NIPS is predominantly are venues which publishes works on machine learning, and VLDB ICD again are venues which publish work on large scale databases. Now for each of these venues, what we try to do is we segregate papers. We segregate papers based on decades. So there is, as we show, we segregate papers into 3 decades: 81 to 90, 91 to 2000, and 2001 to 2010. Now in each decade, what we try to plot is the fraction of citations that is going to that particular decade and the immediate previous decade, the next immediate previous decade, and so on and so forth. So for instance, let us look at this particular bar. So what we observe here, this is the height of the yellow color actually tries to show what is the fraction of citations that is going from the papers of 1991-2000 to the papers of 1991-2000 itself. Then the purple box tries to show what is the fraction of citations that is going from the papers of 1991-2000 to the immediate previous bucket, that is 81 to 90, and the black bucket tries to show what is the fraction of citations that is going to papers beyond 1981. So if you try to see in each of these plots, we try to estimate these fractions and then plot it as stacked bar charts across different fields, across different venues of computer science. Now what you see here immediately, that so in a particular decade, what we have seen in a particular decade, if you look at a particular decade, the fraction of citations that is going to the total fraction of citations that is going to the immediate set of previous decades. Okay, so if you take the purple plus the black, okay, this is the total number of citations that is going to the previous decades, and here you have yellow plus purple plus black, that is going to the that constitutes the total fraction of citations that is going to the immediate previous decades. Now what you see that the total height of purple plus black here is larger than the total height of yellow plus purple plus black. So you see, so this is what actually the Versteeg's paper was observing. The total volume of citations going to older decades is actually higher. So here the total volume of citations that is going to the older decades is higher than here. So this is the total volume of citations that is going to the older decade. But then what they missed is what is the fraction of citations that is going to the current decade. So that actually constitutes the major fraction. That is what they did not observe. They only looked into this part, okay, this part of the data. So and that's why they were observing that this is actually on a rise, whereas they actually completely did not observe this particular fraction, which is going to the immediate, which is going to the current decade itself. And this, now we extend this analysis to the entire computer science field, to another domain of biomedical documents, to a bunch of subfields like data mining, machine learning, artificial intelligence, natural language processing, IR taken together. So this is the data mining, machine learning area. Then you have the hardware area, algorithms area, algorithm, programming language and software engineering taken together. So in each of these what you observe is that, say for instance, take the entire computer science field, the entire computer science domain. So look at the decade 1981 to 1990. The total fraction of citations that is going to the older decades is black plus this blue, whereas the total fraction here in 1991 to 2000 is yellow plus black plus blue. Now the height of yellow plus black plus blue, as you see here, is larger than the height black plus blue, and the height of red plus yellow plus black plus blue is even larger than the immediate previous decades. So that is the total fraction of citations that is going, the total volume of citations that is going to the previous decades, they all taken together is actually growing over time. So this height is smaller than this height, and this is yet smaller than this height. So this is what actually Versteeg was observing. But then there is another fraction which is going to the decade itself, and that is actually the largest chunk, and this is what actually Versteeg's picture does not show us at all. So we here tried to show both these fractions together. So this picture actually reconciles the two facts, the fact that there is a growing number of citations that is going to the older fields because the height is actually rising, but then if you look at the total number of citations going to the current decade itself, that is actually very high compared to what is going to the previous decade. So recent papers actually are getting considerably large number of citations compared to the older papers. So it is not really true that ancient papers are getting a larger fraction of citations over time. So this actually brings us to the end of this particular course. We have tried to see many different aspects, starting from the theory of complex networks, where we have looked into the basic properties like centrality measures, social network roles, etc., to community detection, which is another theoretical perspective of complex networks, and then finally we ended up with a case study where we tried to show applications of all the methods that we have come across so far and how one can meaningfully use this in order to do various quantitative analysis on large scale networks and do various predictions like citation count prediction and prediction of like whether really older papers are getting, ancient papers are getting larger and larger number of citations. So we would end here, and I hope that you have enjoyed the different parts of this course, and I hope that you will find that this course interesting and useful in various applications that you take up from now onwards. Thank you very much.